When the altitude from which an object is dropped toward the Earth increases, then the rate of acceleration changes. An interesting note about the effects of gravity on a skydiver can be seen when, in the year 2012, Felix Baumgartner beat claustrophobia in a record skydive of over 23 miles. Now that is quite a fall. Since potential energy is related to the gravitational acceleration near a large body such as Earth, it only makes sense that the further away from the Earth's surface you get, the less the gravitational acceleration would be, and hence the potential energy would change accordingly. Here is the equation, which is an inverse relationship related to potential energy of an object that is much further away from the Earth than 1 Earth radius. How do you calculate the speed required to leave the Earth's atmosphere and general effects of gravity pulling you back to the surface? You must launch yourself in a rocket at a minimum escape speed. This is the equation for escape speed. Your textbook does additional explanation and derivation work. Notice that the velocity is independent of the actual mass of the object. If you can make a very large object move at least this fast, you can get it to soar off into space and not return. Johannes Kepler was a very patient man. He spent nearly 30 years of his life trying to analyze the motions of the planets. He is especially known for waging war on Mars. The data he analyzed about the orbit of Mars was used to verify his concepts about planetary motion known as Kepler's 3 laws. The law of ellipses: all planets move in elliptical orbits with the Sun at one of the focal points. The law of equal areas: a line drawn from the Sun to any planet sweeps out equal areas in equal time intervals. And the law of harmony: the square of the orbital period of any planet is proportional to cube of the average distance from the Sun to the planet. Kepler's laws were based on observations made by Danish astronomer Tycho Brahe. Sir Isaac Newton later demonstrated that these laws were consequences of the gravitational force between any 2 objects together with Newton's laws of motion. In Kepler's first law, all planets moved in elliptical orbits with the Sun at one focus. Any object bound to another by an inverse square law will move in an elliptical path. The second focus is empty. In his second law, a line drawn from the Sun to any planet will sweep out equal areas in equal times. Notice from the drawing that the areas swept out by each of these lines connecting the Sun to a planet in different time frames of rotation essentially sweeps out the same area during the same time period. This is because the closer the planet is to the Sun, the faster it must be traveling in its orbit. Likewise, the further the planet is from the Sun, the slower it is traveling in its orbit. But it is all relative to the combination of speed, distance, and time. This discovery was essential in determining the final law accredited to Kepler, the law of harmony. Kepler's third law states the square of the orbital period of any planet is proportional to cube of the average distance from the Sun to the planet. It was an effort by Kepler to ultimately describe the motions of the heavens. This link is to a YouTube video which attempts to demonstrate the law of harmony with toy trains. Since we are studying rotational motion, can you see what application and understanding of Kepler's laws might provide for you as a technology student? Now that you have looked at it scientifically, maybe you should think about this. In this lesson, you covered the following objectives.